during the previous lesson, yeah, what we did, yeah, you remember the Young's experiment, yeah, 2 point-like holes, yeah, monochromatic light, and a source which was a point-like, and what we observed in the screen, yeah, was just a set of fringes, yeah, bright, dark, bright, dark, bright, dark, yeah. Then we relaxed the one hypothesis, yeah, the one of pure monochromatic light. We considered quasi-monochromatic light, yeah. So we worked with a narrow band filter, and what we saw is that if you had 2 beams, yeah, coming from a distant source, they could still interfere, yeah, provided that the difference in length of the 2 light paths, yeah, was smaller than the coherence length. Yeah? This means that, well, if you have 2 beams arriving, then well, they get reflected here. So here, you remember in quasi-monochromatic light, we had a wave group, yeah? And so what we should make sure is that the similar wave group, which arrives on the opposite side, yeah, does not arrive too late here. Yeah. So what we want is that it arrives at about the same time. Yeah. And so the condition was just to say, okay, let's make sure that the difference in the light path, yeah, is smaller or equal to the coherence length, which was equal to the square of the wavelength divided by the bandwidth. So we saw that for optical wavelengths, this is typically, well, a few microns. So very high accuracy. Then after what we did, yeah, well, we considered that the source is not point-like, but has some extension. And now, well, what becomes the visibility, yeah, of the fringes? Yeah? Well, we saw that the visibility, which was defined as a difference between the maximum intensity of the fringe minus the minimum one, divided by Imax plus Imin, was in fact equal to the module of the complex degree of mutual coherence, yeah, which was depending on 2 frequency UV. And that, so this module is not always equal to 1, it can be equal to 0 or intermediate values. Then what we established during the previous lecture is that this module, yeah, is nothing else than the Fourier transform, yeah, of the normalized intensity distribution over the source. Yeah? So you remember this was equal to what? To the Fourier transform of the normalized distribution intensity over the source, yeah, well, which depends on the frequency UV. Yeah. And last time, yeah, we reviewed a little bit the properties of the Fourier transform, yeah, and I just reminded, yeah, a few, well, interesting properties. One of the interesting properties that we established was the following: the Fourier transform of the window function, yeah, is equal to what? You remember? It was sinc of S, yeah? So it was the sine of pi s divided by pi s. Then a second property that we established, yeah, it was a similarity, yeah, property, which is the following: that the Fourier transform of a function x divided by a, where a is a real number, yeah, is equal to the module of a multiplied by the Fourier transform of the function fx, but for the variable a times s. So these 2 properties we established last time, yeah? So now, I would like to particularize it. For instance, if you would like to know what is the Fourier transform of the door function x over a of s. Well, I just see the similarity, yeah? So I just say, okay, it will be module of a times the Fourier transform of the Dor function. But the Fourier transform of the Dor function is this one. Yeah. So it will be, but evaluated not for the variable s, but for the variable a times s. Yeah. So it will be multiplied by sine pi as divided by pi as. Yeah. Okay. Now at the end of the previous lecture, yeah. Well, I just asked, yeah, well, would it be possible for you to think about the solution of what should be the visibility for a square star? Yeah. So the star is square, like that. Then I think the width, yeah, or the side, yeah, was zeta 0. Yeah, something like that. And so we know that the visibility is equal to the module, yeah, of the Fourier transform of what? Well, of this function, which depends on the coordinate zeta eta, and as a function of the frequency uv. Yeah, because I didn't consider it last time. The Fourier transform of the Dirac function is equal to, yeah, this is very interesting, yeah. So, well, it is integration from minus infinity to plus infinity of the Dirac function of exponentiation minus 2 pi x s dx. You agree? So, this is easy. It is just the value of this function for x equals 0. So, it's equal to how much? 1. It's equal to 1. Which means, now let's take the inverse Fourier transform of 1, and we will recover delta x. Yeah? So delta x, you agree, is equal to the inverse Fourier transform of the Fourier transform of delta x. Yeah? You agree? The inverse Fourier transform of the Fourier transform gives you back the function, yeah? So it is equal to this one, to integration from minus infinity to plus infinity of the Fourier transform of delta x, it is 1 times ei2 pi xs ds. Yeah? And you see, this is a very amazing, yeah, representation of the expression of the Dirac function, yeah? Yeah? So, well, this is true for, well, some kinds of distribution. So this is what is shown here, that the Dirac function, yeah, can be expressed as follows. It's the inverse Fourier transform of 1. Interesting. Now, well, I propose, yeah, more applications. I think it's important, yeah. So the next application is the following, yeah. Let's consider the case of a double star. So now we observe with an interferometer, yeah, a star in the sky, and we assume that we know the model. It is a double star, but we don't know what is the separation between the two. And we would like, from our measurements, yeah, to precise what is the angular separation between the two stars. Yeah. Okay, we assume, well, to make it simple, that they are equally bright, but we could relax that hypothesis. It would make, well, the problem technically a little bit more difficult, but still. I remind you that the visibility, yeah, is the module of the complex degree of coherence. Well, in this case, yeah, it's just a one-dimensional problem, yeah, so it's very simple, yeah. This is equal to the module of the Fourier transform of the normalized intensity, yeah, of the object. Yeah. Now I know I have a double star equally bright. Yeah. So I should find what is I prime as said before, yeah, well, this is equal to I zeta divided by the integration of I zeta d zeta. You agree? Yeah. Okay, now I zeta, I could say, well, since the separation is 2 zeta 0, that, well, it is simply delta zeta minus zeta 0 plus delta zeta plus zeta 0. So this is a nice way to represent a double star, yeah? So one is located at plus zeta 0 and the other one at minus zeta 0, yeah? Now if I ask you, is it normalized, this intensity? No. When I integrate, how much do I get? 2. So easy, I divide by 2. And I can say, okay, now this is a normalized intensity. Okay. So now I just calculate the visibility. So it's a module of the Fourier transform, yeah? You see, of two functions. So it is a summation of two Fourier transform of each function, yeah? So it will be summation of the Fourier, so there will be 1/2 times the module of the Fourier transform of delta minus zeta 0 I would say like that, delta zeta minus zeta 0 of u plus Fourier transform of delta zeta plus zeta 0 of u. Do you agree with that? Yeah. Now, here, yeah, well, I could, as a preface made by you, well, make the full analytical development, yeah, but I like the properties, yeah. And now I remind you, we established last time, yeah, the translation property, yeah. So the translation property was the following. So this one we had demonstrated here. It is equal to the exponential of minus 2i pi xs multiplied by the Fourier transform of the function fx of s. You agree? So here we just apply it. So we say, okay, is equal to 1/2 times the module. Now the Fourier transform of that one, just make use of that property, yeah? So it will be the exponentiation of minus I 2 pi, yeah? Then zeta 0 u multiplied by the Fourier transform of the Dirac function. How much? 1 plus exponentiation. So I apply as a translation property. So plus I 2 pi zeta 0 u multiplied by the Fourier transform of the Dirac function, 1. Yeah. Okay. Now, this is easy to solve, yeah? Because it's cos minus I sine plus cos plus I sine. So the imaginary, yeah, contribution disappear, and what remains is 2 times, but divided by 2, so it will be 1. So it will be the cosine, module of the cosine of 2 pi zeta 0 times u. Like that. You agree? Okay, now if I represent, yeah, the visibility as a function of the frequency u, well, it will be a cosine, yeah, so the maximum will be 1, visibility, then it goes to 0, comes to 0, and again and again. And now, if I would like to know for which value of u I have a 0, I'll just say, okay, this is when 2 pi times 0, zeta 0 u will be equal to pi divided by 2. So the pi simplify, the 2 here becomes a 4. So I find that u will be equal to 1 over 4 zeta 0. Correct? Yeah? So this is 1 over 4 zeta 0. Yeah. Now we could make another exercise. Yeah? So here we just took a model and we calculated visibilities. Now I will do the opposite. I will assume that I'm observing, yeah? I'm observing a star, and I find the visibility as a function of u. So here I just erase all of that. So now let's assume, yeah, let's assume that, oh yeah, this is visibility 1. Let's assume that I make visibility measurement. I look at an object here, and this is what I obtain here, then here, then here, then here, and then this is what an observer would do, yeah? He would look at that and say, whoa. You say, wow, this looks like a cosine, yeah? So I would say, okay, the visibility, yeah, looks like the module of the cosine of what? Here I would say, okay, a constant alpha times u. And I know the value of alpha. I know the value of alpha, yeah? Now I would like to, so I assume that, okay, this is analytical expression representing the visibilities I'm observing, yeah? Can I infer now, yeah, what is the structure of the source? Yeah? Can I infer now what is the structure of the source? Well, the answer, yeah, is the following. You remember, yeah, the visibility is a module of gamma 1, 2, is a module of the Fourier transform of I prime, like that. Now I could say, okay, so I prime is an inverse Fourier transform, yeah, sure, of what? Of gamma 1, 2. Yeah. Now, what you see here, you don't have the module, you don't have the complex degree of mutual coherence. You only observe the module. Yeah. But you'd say, okay, I assume that gamma 1, 2 is equal to cosine times alpha u. Indeed, because, well, the module would be equal to the module of cosine, yeah? So this is a natural assumption, yeah? And now can I find the solution? Well, let's try. So I would say, okay, this is equal to integration from minus infinity to plus infinity, cosine of alpha u multiplied by exponentiation of, now it's not a minus, it's a plus, because it's an inverse Fourier transform. Yeah? So it will be I to pi u, then zeta times d zeta. You agree with that? Okay, now how to go on, yeah? Well, to go on, I would do the following. I would say, okay, cosine, yeah, it's equal to 1/2. Sorry?
Instead of dz, du?
This is a du. Yeah, yeah, it's a du. Yeah. So the cosine, I would say, is equal to 1/2, yeah, alpha u plus e minus I alpha u. You agree? So I could say that this is equal to 1/2 integration minus infinity plus infinity of oops, Now I will distribute, yeah, these two terms. So I will find that it's EI multiplied by alpha plus 2 pi. Okay, now I don't like that way, so I will do it differently. I will say 2 pi multiplied by alpha divided by 2 pi. Okay. So this is the first one. Now I need that one plus u plus u zeta. Correct? Well, I guess, huh? Plus u zeta du plus 1/2. So I just put a parenthesis. Integration from minus infinity to plus infinity of e 2 pi. Now minus alpha over 2 pi plus oh, here I made a mistake, yeah. So I put it like that. And here it will be plus zeta times u du. You agree? Okay. Now, what can I say from here? You remember, well, I will make use of that one. Correct? So I just say, okay, this is 1/2. So this will be delta of zeta plus alpha over 2 pi plus delta of zeta minus alpha over 2 pi. Yeah? And now I say, oh, this is a double star, yeah, because the two Dirac functions which are separated, yeah, by alpha over pi. This is the angular, yeah, distance between the two. So I would say, okay, the separation between the two, yeah, is 2 zeta 0 equal alpha over pi. So you see how it's possible, yeah, from, well, a few data points you have, yeah, to retrieve some properties, some physical properties about the source you are looking at, yeah. But I made implicitly use, yeah, of an a priori model. Because I have so few data points, 1, 2, 3, 4, and well, I found the solution. It's a perfect model, but sometimes it's much more complex than that, yeah, because you could have a star with a disk or a double star with different flux ratio plus a disk plus etc., yeah. So this is the ingenuity of the people making, you know, optical interferometry, yeah? From a few data points, yeah, they find well, nice constraints in the model, yeah. Now, if you would have many data points, yeah, well, then you can perform, yeah, a perfect inverse Fourier transform and find the real intensity distribution of the source. But for that, you need many data points, yeah. And this is the strength, yeah, of arrays like VLA in the radio or DMRT, yeah, that you get at the same time many UV measurements. You don't have the phase information here. Yeah, I didn't address that point yet, yeah. But if you like, during a subsequent lesson, yeah, I will show you how it is possible, yeah, to address, well, the phase information, yeah, yeah. Well, just to answer your question, yeah, very, very rapidly, yeah. You remember that in the experiment of Young's holes, yeah, what we found is that the intensity, yeah, is equal to 2 high for quasi-monochromatic light, yeah, 1 plus module gamma 1, 2, 0 times cosine of 2 pi nu tau minus beta 1, 2. Yeah. So this is what we found during the previous lesson. And what you are telling is about this phase information. So for the moment you see I didn't make use of phase information. But indeed you could make use of phase information, but for that you would need at least 3 telescopes. And I will address that point later. But if you have three telescopes, you consider telescope 1, 2, 2, 3, and 1, 3. And by combining that information, you may make some use of this phase information, and this will help you in the reconstruction of the images. So I think that the first who addressed that problem properly was Gerd Weigel, maybe 25 years ago. How at optical wavelengths make use of the phase information, and he just got inspiration from what people were doing in radio astronomy. Because it was a bispectrum. You heard about bispectrum theory to address this problem. But this I will come later. So here. What is the problem? Is that when you observe fringes in the screen, so you see the fringes like that, but you don't know whether it's here or there. This is the problem. And this gives you some information on beta 1, 2. Now, if you have only 2 telescopes, you cannot find the phase. If you have 3 telescopes, you can retrieve some information of the phase due to the source. Because the problem is that the atmosphere induces some contribution to that, and you have to get rid of the atmospheric effect. This one we just did. Now, this is a second nice application, which is, try to derive the visibility of the interference fringes measured with the same interferometer, but of a one-dimension Gaussian star, which intensity distribution is given by the following expression. So you see, we assume now a model, and we wonder what is the visibility like. Now, we won't make it now because it's technical, it's not difficult, but you need to make use of that. The following information. First is that if you integrate a Gaussian profile of that type, this is a solution, it's classical, You did that during your high school studies, probably, So since you have to normalize it, you will have to divide this expression, by that one. So then you get a normalized Gaussian distribution. And now what you should also be able to establish, it's not difficult, is that the Fourier transform of a Gaussian, is still a Gaussian. It's another Gaussian, So it's very easy, Now the solution, I give it to you, but you may try it at home, You would find that the visibility, is given by the following expression. And you see, this is important to realize, that all the visibilities, should be such that for the value of the frequency u equal to 0, the visibility should be equal to 1. Always. Always. And there is a good reason why it is like that, But you have seen when I showed the visibility here, for u equals 0, the visibility was equal to 1, because you don't resolve the source, If you put 2 telescopes of an interferometer close to each other, the baseline is 0, so it's impossible for you to resolve the star, So visibility will always be equal to 1. So when you make these exercises, if you find a visibility which is not 1 when u is equal 0 or v equals 0, it means that you have a problem. You have to find what is the solution. But now, what you see here is that the full width at half maximum here was at the denominator, and now the full width at half maximum, when you make the Fourier transform, is at the numerator, Which means the following, The narrower is the angular size of the star, broader its visibility content in angular space frequencies, And indeed, we know that if it is a Dirac function, So extremely narrow. Well, the Fourier transform is equal to 1. So you have containing frequencies going from minus infinity to plus infinity. Yeah. So interesting. So this is just an exercise that I suggest to you to do at home. Now this one we did, yeah. Well, you came to the blackboard and made it, yeah. And now, well, I just say a remark, yeah, to check whether your original function I, which depends on zeta and or eta, has been properly normalized. See whether its Fourier transform for u equals 0 and or v equals 0 is equal to unity. And why? Why is it so? Yeah, I will show you directly here that the integration of I prime zeta d zeta is equal to 1. Okay? So I assume that it is equal to 1, yeah? Why should the visibility also be equal to 1 when u is equal to 0? Easy, look. If I make the Fourier transform of I prime, is equal to what? Well, it's integration from minus infinity to plus infinity of I prime zeta times exponential of minus I2 pi zeta u d zeta. Agree? Now, if I set in this expression, yeah, u equal to 0, yeah, so I calculate, yeah, ft of I prime zeta for u equal to 0. Do you agree that this is equal to the integration of minus infinity to plus infinity? I prime zeta for u equal to 0, this is equal to 1. So I find d zeta. Yeah? But this is equal to 1. Yeah? So this is what I had to demonstrate. Yeah? So here I just demonstrated that whenever your function has been normalized, yeah, your visibility should always be equal to 1 when u is equal to 0. Yeah? If you make it multidimensional, it's still the true. Well, it's still valid, of course. Yeah? Now, I think this exercise I will do because it's technically difficult. And it is a case for a circular star, yeah? So for a real star, yeah? So as I write, yeah, a generalization of the previous application for the square star, yeah, consists in deriving the visibility of a star which is seen as a projected two-dimensional uniform circular disk, which angular radius is rho, ud, uniform disk, or its angular diameter equal to theta ud. So how to do that? And therefore, yeah, I had asked you, yeah, whether if you had time to revise what is a zero-order Bessel function, first-order Bessel function, yeah. So it comes now into the game, yeah. So you agree that what we want to do is to calculate gamma 1, 2 of uv for the frequency uv, yeah, which is equal to a double integration from minus infinity to plus infinity of what? It's not a square star, but it is a circular one with, well, a radius, yeah, equal rho ud. So it is 1 inside and it is 0 outside, but still I should normalize it, yeah? I should normalize it, yeah? Then Fourier transform of I2 pi of zeta u plus eta v. Now d zeta d eta. So do you agree that here, yeah, I say, well, it's I prime of zeta eta, but for the case of a circular disk, yeah. Okay, now so how to do? Because of the circular symmetry, yeah, it's good to use polar coordinates, yeah. So first of all, yeah, I define u, which is equal to x over lambda, as being equal to rho times cosine of, well, psi divided by lambda. So I make change of variable, of course, v equal y over lambda, and y, I just set it equal to r times sine psi over lambda. Now I need also to do something similar for zeta. So I say zeta is equal to theta times cosinus phi, eta equal theta times sine phi. And now, would you agree that here I can write, well, it will be this integration. So considering for this one, yeah, I will go from 0 to rho ud. So this is the angular radius, yeah, of the star. Yeah. Now here, d zeta d eta, yeah, well, there will be a theta times d theta. Yeah. After, I will integrate from 0 to 2 pi. And here the angle should be d phi. D phi like that. So well, it will come somewhere else. Now time exponentiation of minus I2 pi of zeta. So it will be there will be some theta times cos phi times u, but u it's r over lambda, r over lambda. So I can do it like that, time cos psi plus eta. Eta, it's theta here, times sine phi, multiplied by v, it's r over lambda, good, times sine psi. And now d phi. Okay? But my intensity should be normalized, yeah? So I should divide by the area of the stellar disk, yeah? Which should be 1 over pi times rho ud square. Correct? Okay, now, do you remember this quantity, cos plus sine sine? Is? Yeah. So it will be cos phi minus psi. Yeah, right? Now, well, I continue. Yeah, I will make some, still some variable changes. Yeah, I will pose that z is equal to 2 pi r over lambda times theta. So still a change of variable, yeah. And now still another one. I will pose that phi minus psi is equal to half pi minus a big phi. Yeah. So this previous equation will simplify as follows. It will be 1 over pi rho square ud multiplied by the integration of 0. So I make the change of variable, yeah? So it will be to 2 pi times r theta ud, rho ud here, rho ud divided by lambda. Theta d theta. Well, theta d theta will be z dz, yeah? So now I will have something like z times dz, but I should multiply by lambda over 2 pi r square. like that. Yeah, okay? Now, I continue. So it will be the integration of what? Wow, here it's a bit more complicated. So phi will be equal to half pi minus phi minus c. Yeah. So it will be the integration here. And then when I find that d phi, or d phi, yeah, big phi, is equal to minus d small phi. Yeah. So here it will be the integration from, I just take 2 pi. So here it will be minus 3 pi over 2. Yeah, phi. So I'm trying to, if I take 2 pi, it will be minus 3 pi half, and plus psi. And here, since it is 0, it will be half pi plus psi, like that. Now, this one will be the exponentiation of minus I times z multiplied by the cosine of that quantity, but the cosine of that quantity will be the sine of big phi. Okay? And now, well, here I can write d phi, like that. Okay, now, this one, yeah, I can develop it as follows. I can say that it's a cosine of z times sine big phi minus I times the sine times z times the sine of big phi, like that. Now here, this is interesting to see that I integrate, yeah, from this value to that value. So I make a complete term. Okay? So in fact, it doesn't depend on phi. I can take it away. I can put it that I go from 0 to 2 pi, it would be the same. Yeah? Okay? Now, here I see that this is order function of phi, which means that its contribution will be 0. And here I have an even contribution, yeah? When I integrate for negative values or positive value, it will be the same because of the cos, yeah? So, at the end, what I may write is that these all expressions will be equal to lambda over 2 pi r square times 1 over pi rho ud square times the integration from 0 to 2 pi r rho ud over lambda. Now here it's z, or the dz, I will write it here. And then I continue. I just say, okay, times twice the integration from 0 to pi. Because, so this contribution will be 0. This contribution, yeah, is even, yeah. So it's twice the contribution from 0 to pi, yeah, of the cosine. No, now I can write z times the cosine, or no, I write z here, times the cosine of z sine big phi d phi, like that. So I hope I didn't make a mistake, yeah? Now what I do, I divide this by pi, so I have to multiply it here by pi, and here I recognize the zero order Bessel function. Yeah. So this is J0 of the variable Z. Okay. Now I will make use of another property, which is the following one, is that the integration of x G0x dx is in fact equal to x times G1 of x. So here I just put prime. Okay, so this is a property of between the zero order Bessel function and the first order Bessel function. And it's because, well, I have here this and this, so I find it normal. So that it is equal to lambda over 2 pi r squared times 1 over pi rho square ud multiplied by, well, I have 2 pi, which is 2 pi. And now I have to apply this property. So I can say, well, it will be equal to 2 pi. So the x, which is this upper limit of integration, so it will be 2 pi r rho ud divided by lambda, multiplied by the first order Bessel function for that same value. So 2 pi r times rho ud divided by lambda, exact. So if I didn't make a mistake, Now what I do, look, I divide this by 2 pi r rho ud over lambda. This one, I can put it square, because I will have simplifications there, And now, well, I try to still simplify it, So it's almost down. So I take another color, and I show you that, so this quantity and this quantity will neutralize, Very good. Now, 2 pi r over lambda and 2 pi r over lambda here will neutralize also, Very good. Now, the pi and the pi neutralize, and what is left, is that it's equal to 2 times G1 of 2 pi r. So now I can write it pi times r, and now instead of the radius, I just put the diameter, the angular diameter of the uniform disk over lambda, divided by pi r theta ud over lambda. And this is the gamma 1, 2 for 0. And now, well, the parameter I have here, well, I could say, well, it's r over lambda, like that, where r is the separation between the two telescopes. Okay? So there is any azimuthal dependence, of what I'm measuring. And, well, it's not surprising because of the symmetry of the problem, So the azimuth angle has disappeared. Well, it has disappeared here, you see? Okay, now if I take the module, and this is what I obtain. I obtain that the visibility of the fringes when I observe, a star, is just given by that expression, And, well, this is very, very, very often applied, by people when they observe single stars, they're measuring their angular diameters, Now, well, it's interesting to know that J1 over x, the limit when x goes to 0 is equal to 1/2. So this is a property, yeah, of the zero-order Bessel function. Yeah, when x goes to 0, this quantity goes to 1/2. It means that when r, the separation between my two telescopes, yeah, goes to 0, this goes to 1/2 times 2, it's 1. So I find visibility of 1. So I know I didn't make a mistake. Yeah, yeah, yeah. And now, well, I just come back to my presentation and show you, well, the result. Yeah. So we see in many papers which have been published here in optical infrared interferometry, yeah, those results. Yeah. So here, well, I will go very fast, yeah, because the whole demonstration is here in the notes, yeah. So I did that during the weekend, yeah. So, okay, these are the properties. Now, very important is that the Bessel function, yeah, first order, yeah, gets 0 for the value of, let's say, remember, 3.8, yeah. Okay, now I go here and I show you the result, yeah. So this is the visibility, the module of the complex degree of mutual coherence, yeah. And I find that, wow, for the value of 3.8, yeah, it goes to 0, yeah. Which means the following, yeah, is that when pi times r times theta ud over lambda is equal to 3.8, about, yeah, well, the visibility is 0, yeah, so I don't see fringes anymore. So I know that I'm resolving the star, yeah. Now let's do the following. I divide by pi here. Then I multiply by lambda. And I divide by r. And 3.8 divided by 3.14, yeah, is 1.22, yeah. So this is a magic 1.22 lambda over r. So I see that when we make, yeah, we look at a star, we assume that it is a uniformly bright disk, even by making one measurement, yeah. If your approximation is correct, yeah, so you assume that the star is a uniform disk, yeah. You just make one separation between the two telescopes. Here, I make one visibility measurements, yeah, so I got the value. And then I just fit a curve through that point from one single point, yeah, and I'm getting the angular diameter, yeah. Now, what is better is to make several points, at least 2, so that you know you don't make a mistake. And indeed, yeah, what people found out very easily, yeah, is that it would be important to include a limb darkening law, yeah, for the stellar limb, yeah, because it's not uniformly bright, yeah. But it's not difficult to do. So, in conclusion, before the break, I draw your attention, yeah, to, yeah, this very nice lines. Yeah, the face of truth is covered with a golden disc, unveiled, yeah, awesome, so that I, who loves the truth, may see it. Yeah. So, in our case, it would looks like that. So this is a golden disc, yeah. And now you want to unveil the disc, yeah, and see what is the truth behind, yeah. Well, in our case, it would be that the visibility of the fringes is a Bessel function divided by that, yeah. Okay, so we make the break now, go for tea, and after we continue. If there is any question now, but this is a very, well, technical, you have seen how much it was technical. The case of the square star, yeah, was much easier, yeah, to get, technically speaking, yeah. And so, well, for those who later, yeah, who could make some, well, use of interferometric, well, theory or observations, yeah, you would advise you always to work with the rectangular or square elements, you know, even your telescope, everything. Then you find the answer, which is very close to the truth. Now, if you want to get it correct, you should apply circular symmetry. And what is a sinc function, cardinal sign, yeah, becomes a first order Bessel function. That's all, yeah.